CyNam's tech showcase all about ransomware. And thank you for joining us. I believe we've got a large number of people joining us today, and it's fantastic to have our friends and colleagues from Edinburgh Napier University to talk about their NapierOne data set and how that can help develop anti-ransomware solutions. And I think it'll come as a surprise to absolutely nobody on this call of the growing threat from ransomware as attacks become more sophisticated, as the impact of those attacks become more complex, and the ransoms that are being demanded seem to be increasing year on year. And I think those events in Eastern Europe at the moment as well are also having an impact on the threat we face. So it's very appropriate that we bring you today the work that's being done under Professor Bill Buchanan and his team at Edinburgh Napier University. I'd like to introduce you to Simon Davies. So he's the brainchild behind the NapierOne data set, and I'll let Simon sort of tell you all about that as well. We're also going to be joined by Rich Macfarlane, also working at Edinburgh Napier, and Bill Buchanan is here with us as well. So it's a real good opportunity for yourselves, whether you're involved in cybersecurity from a mitigation perspective, whether you're developing ransomware detection capabilities to ask these guys questions, understand how this data set could be used to help develop and research into new capabilities in that space. I think it's also worth stating before I hand over to Simon as well that the ransomware challenge is a major challenge for the NCSC as well, to the extent that they've now released their latest challenge for the NCSC for Startups program, which is focused on ransomware. So looking for startups that are developing capabilities in the space to join the accelerator program and help take those capabilities further. And they're looking across three areas. One is around sort of backups and how to recover from ransomware. The other is around solutions on ransomware detection. But then equally, they're also looking at solutions that are affordable for the small to medium sized business market, because ransomware is a threat that impacts businesses of all shapes and sizes. So if you are a company that's developing capability in that space, please do get in touch with us, and we'll let you know how to apply to join that program. Okay, so that's enough from me in terms of an introduction. As I say, I'm delighted to be joined by Simon Davies from Edinburgh Napier University. Welcome, Simon. Thank you for talking to us today. I'll hand over to you and Rich Macfarlane. And yes, please, folks, add your questions into the chat box, and we'll start to answer those as we go through the presentation. Over to you, Simon.
Thanks, Rich, and thanks everybody else for sparing the time today to come and listen to our presentation on NapierOne dataset. So this is a dataset that's resulted from our research, and we've developed it over the last year, and it's being information is now being published in one of the research journals. So let me get my slides back working. So today, what I plan to do is give you an introduction to us and the team and what we were doing, and then a background into our research, and then discuss a little bit about the creation of the dataset and what it contains, and possibly how you may be able to use it. And then towards the end of the presentation, I'll give a demonstration of how you can access the dataset. And then finally, we'll take questions at the end. And then after that, I think we'll discuss a little bit about other research that we're doing in ransomware detection and analysis. So a little bit about myself. I'm a third-year PhD student studying at Edinburgh Napier University in the School of Computing. And I think somebody will post contact details for us and the team in the chat at some point during the presentation. If not, please feel free to reach out to me at simon.s.davis@napier.ac.uk. So to start with, we've been researching ransomware, and in general, ransomware is a growing problem within many areas of industry, specifically in the computer industry, but also in infrastructure and medical and government. And every year it seems to broaden its attack surface and deepen and become more and more prominent and more of a problem. So in general, what ransomware is a program that somehow ends up on your computer, and it then encrypts the files and will only give you access back to the files or back to the whole computer once the ransom has been paid. And as I said, the issue of ransomware is a growing concern, and the amounts of money that have been taken from victims is also growing every year. And here's one prediction that I found recently, where they're saying that the cost is increasing every year, and also the frequency of the attack, and also, as I said, the area of attack. So our team, we've been working on many aspects of ransomware research, amongst which is analysis, so analyzing how ransomware behaves once it starts its infection, and maybe using this behavior to indicate that you have a ransomware attack, ongoing ransomware attack, and then use this indication to intercept or disrupt the attack or mitigate the attack. So we're using several ways currently of using the detection or using techniques or behavior of ransomware to detect its presence. One being entropy of files being created, because encrypted files tend to be more complex or more higher entropy than regular files used on the system, on computer systems. So we're using entropy changes in file systems to detect attacks, but also process behavior, such as very, very large file scans, or very many read-write operations performed by a process that shouldn't really be doing this sort of action. And we can use these as flags for further investigation. And we're also working on mitigation of attacks. So once some files or all the files have been encrypted, if there are any side channel attacks that we can use to possibly revert these changes or recover the files that have been affected by a ransomware attack. So during our research, we came across many situations where we found solutions that people had developed, but it was very difficult, if not impossible, for us to reproduce their findings and also analyze how they've worked, basically because the data sets that they've used were not available not publicly available. And because of this, it was very difficult to validate the findings of these papers. And if we could not validate them, then it was very difficult to see if the results produced by these tools and techniques were actually useful in a real-world situation. So we proceeded to design and develop a data set, because the data sets that were available for research were limited in existence and also in content. The most common data set currently used in not specifically ransomware, but also malware analysis is the GovDocs1 data set. The problem with this data set was generated from scanning or scraping the US government websites for file types and then assimilating these into a data set. The problem was with this, or is with this data set, is that it's currently now 12 years old. So many more modern file types are very badly represented within the data set. For example, the docx or the pptx or the new xlx formats have very few examples in that data set. The majority of the data set contains HTML or the PDF files. There are some more modern data sets, the T5 and the MSX data sets, which are also used in some research. These data sets are based on the GovDocs1, but have been enhanced to contain, the data set has been reduced in size, but enhanced in content. So now these data sets contain docx or similar Microsoft formats, modern Microsoft formats. But time moves on and file type usage also changes. So when we decided to develop our own data set, we first had to decide what could be contained or what should be contained in this data set. If we wanted a data set to contain the the most common files available or used in the world today, we first had to decide what those most common files were. So the first part of our research was to conduct research into trying to identify what the most common files in use today were. And we did this using a sort of a broad, but I've forgotten the word, but a broad research base, and then using the files that were mentioned most in most of these data sources and combining them together. So the most common files that appeared in most of these data sources appeared then in our database. So we looked at virus total and see the frequency of the files that were submitted to virus total. There is also a website called W3Techs, which monitors and records the uses of different media files on the internet. We then also analyzed Google's search statistics to look at files present in the indexing of Google while it scrapes or crawls the internet. We also then reviewed file preservation research, which is an area of research used to determine what are the most common files in currently used today and how to preserve the content and how to allow reading of the content in the future. So in a way, they're also identifying what the most useful files are on the internet today, in use today. We then also gathered MIME type statistics, which is a file type statistic used to define files on the internet. We gathered these from sources such as Wayback Machine and Webcrawler. There are also several other websites, for instance, fileinfo.com or fileextension.com, which also gather statistics about requests for file types and how to open these types. So they also have lists of how often a certain file type is requested and things like that. And then we also analyzed operating system installations to look at what files are present in these installations and typical Windows or a Linux installation. And then we also categorized those and classed those. So then together we came together with all these and some other attempts. We made a consensus approach. So if when searching one of these sources, the file type appeared as well as in others, then we brought those together and generated what we considered to be a reasonable representation of common files today. We don't think it's a definitive list, and we don't claim it to be, but this is what we found from our research. And the file types that we found, we came up with 44 different file types that we found. And I've put some of them on. I put them all on the slide now, so you can see what in our research from those sources we believe to be a representative selection of files. And from this list, this is the basis of the data set for NapierOne, and we've attempted to gather at least 5,000 examples of each of these file types, and we've accumulated those or aggregated all these into this NapierOne data set. What we've also done is we've created some metadata sets where we've created, in one respect, we created a file tree of 5,000 directories, and then we populated each of these directories with a selection of files that we've gathered, for example, docx or xlsx or PowerPoint or plain text files. We've populated these 5,000 directories with those files, and then we've used compression algorithms to compress these directories. So then we'll have 5,000 examples of a gzip, for example, compression of these 5,000 directories. So then we have a meta source of file types in the data system. One advantage of this is then we'll have within the same data set, or within the NapierOne data set, we'll have both the source files for the compression, but also the result of the compression. So you have a little bit of usefulness there. You can use the data set to, in some ways, compare different compression techniques. So, for example, the first directory in the gzip file data subset is the same as the first directory in the zlib compression, and so on and so on. So this meta data set is also useful when comparing different compression techniques. We've also created a directory that had 5,000 common files, for example, the XLS or XL or PPTX, or other typical files that are attacked by ransomware. And then we've exposed those files to different types of ransomware. Currently, I believe it's 8 different strains of ransomware. So then we have 8 sub-data sets within the NapierOne dataset that contain 5,000 files encrypted with 8 different ransomware strains. And again, you have then the possibility to compare the results of a file being encrypted using a specific strain of ransomware together with the original file or the source or victim target file of that ransomware. So you can see in a way the before and after of a ransomware encryption of a specific file. So once we'd identified the files that we needed, we had to go on and then try and determine where we can get the files from or where we can source the files from. So as a base level, we copied the technique used by the developers of the GovDocs1 dataset, and we started by scraping or analyzing the files that are available on the gov.uk website. And we were able to source many files from that source, from the gov.uk domain. But we couldn't get all the file types from that domain, for instance, operating system files or EXE files and things like that. So then we've also sourced them from other areas and other publicly available data sets. So for example, the MP4 image compression file type we've taken from the free the kinetics data set. And then we've taken, for example, one of the and so for instance, some of the image files, while we've got examples of image files from the RAISE dataset, we also have example image files taken from Common Crawl or common websites that have been indexed by the Common Crawl process. So that's basically the fundamental of the data set. So we've analyzed and determined a list of file types that we believe to be in common use today in systems, and we've also identified places where we can source the data set. So as an overall picture of the data set, we have this diagram here, and in the center where you see the little file folders icons, you can see all the data types that we have in the data set. And then from the left, you can see where those file types have been sourced from. So for example, if we look at HTML, we can follow the black arrow back, and we can see that that's actually been sourced from the gov.uk dataset. Or if we look at TIFF, for example, we can see that that's been sourced from the RAISE open dataset. Then on the right-hand side, we have other arrows. So for example, with the images, one sub data set of these images are derived from each other. So we have if we look again at the TIFF data set, we can see that the line comes from the TIFF data set and goes in into example the web.p. And this arrow indicates that we've taken as a base data set the content of the TIFF file, the TIFF data subset. We've then converted it to WebP format, but we've also converted it to SVG format and PNG and JPG and GIF and EPS and DWG and BMP. A side effect of this approach is that, for example, every file, for example, the first file in every one of these data sets is the same image, but in data formats. So one use of this approach is that you're able to compare the compression techniques or the rendering techniques of each of these different formats together. So you can look at the file size and the quality and, for instance, the entropy of each of these different compression techniques. We have also sourced, if you look again at, for instance, this web.p, sorry. So we have an example of a converted TIFF file in the web.p, but we also have, if you follow the arrow up, we have examples taken from the Common Crawl data set, which is a accumulation of files gathered from the internet. So we have a subset to the WebP dataset, which contains a converted TIFF format, but also another subset that contains WebP images as well. And then looking again on the right-hand side of the diagram, we can see that we've created file collections here from docx, JPEG, PDF, PPT, PPTX, XLS, and XS. And this is where we were creating this file structure that I mentioned earlier, 5,000 directories. And these 5,000 directories were then compressed into 7-zip archives, gzip archives, RAR, TAR, zip, and zlib. This compression, we've used multiple versions of these compression algorithms. So for example, in the 7-zip, we would have deflate compression, we'd have LZMZ, and several others. So there are sub data sets within this 7-zip data set that contains different implementations of the 7-zip compression using different compression techniques. So this is a graphical representation of how the data set is, what it contains in general, how it was sourced, and how they relate to each other. So an example of how the files have not retained their original name, we've implemented a naming convention to allow visually for the file name to in some way self-document what it contains, but also document how it relates to other files within the data sets. So the basic naming convention is we have a sequence number, which starts from 0, starts from 1 and ends on 5,000. Then we have the original extension of the file, and the reason why we have that is because when a file is attacked by ransomware, it can change its extension. So using this naming convention, we can determine the original format of the file. We have a field within the file name for extra information, and then we have the extension of the file that it currently has in that data set. So for example, with this file name here, we have 01, which indicates it's the first member of the docx dataset, and it's password protected, and it has the docx format. So if I just go back to this diagram here, we see there's a relationship here between the TIFF and all the other image formats, and this is graphically represented in the next slide here. So in this slide demonstrates how the files are all how many image data subsets there are and how they're related. So we have the base image here from TIFF. From this TIFF image, a bitmap image is also created. From this TIFF, an EPS is created. Again, a GIF is created and a JPEG file. But also within the JPEG data subset, there are subsets. So we have a JPEG image with 0.1% quality, 25% quality, 50% quality, 75 and 100. So we have 1, 2, 3, 4. We have 5 instances of the same image using different JPEG compression quality settings. So again, you could use in this data set, you could check quality of the image, file size, compression, etc. And then the same again with the PNG, we have compression 0, 3, 5, 7, and 9. So for example, in this compression 5, the image with sequence number 0001 would be the same image as, for example, in JPEG quality 75 with sequence number 0001. So again, there's a linkage and a relationship between the files in the data set. So that could be also a point of research. So the data set could be used as a point of research. Then we also have SVG, and then we have WebP with lossless and 50% quality compression, and then different compression levels on those as well. So this is a graphical representation of one part of the data set and how the relationship is between them. And then linking this to the file naming. So for example, we have, I'm not sure how many we have here, 20, 25 different image files. These are all individual files within the data set. And we can see here the 001 on all the files. So that indicates the first file in the data set. But to us, it also indicates that the actual base image is all the same. And the base image is this 001 TIFF. But then we have this TIFF resize, which is a smaller size TIFF formatted file of this file, and so on and so on. And here we can see the sequence number, the original extension, an optional information section for the file name, and the file extension itself. So using this naming technique is convention, it's very easy to see how these files relate together, and also what content they have, on what compression they have. So we have PNG with compression 9, and it's an original PNG file. And from the 01, we know it's the same as all these other files here. So we sourced the files, we've grouped the files, and then what we did then was then we analyzed all the files, because we didn't want to be responsible for distributing a dirty or an incomplete data set. So the first steps we did was everything was scanned with the latest version of virus checking programs to confirm they're okay. Then any file that could conceivably contain a virus or malware was then uploaded to VirusTotal. So we uploaded probably about 350,000 files. These have also then been checked by VirusTotal and confirmed to be clean and free of any known malware or viruses or ransomware at that time. The resulting files were then format checked. So they are confirmed that they could be opened by the associated program. So for example, a docx could be opened by a Microsoft Word, and a PDF could be opened by a PDF reader. The format was then checked in detail, so it confirmed that the magic number of the file, which is the first few digits of a file that identifies the content of the file or the format of the file. So these are all checked, and then confirmed that they adhere to the right standards for that file type. And then the video files that were sourced from the internet, and the image files that were not sourced, that were not converted from the TIFF, were also then visually checked to confirm that they didn't contain any inappropriate material or any contraband material. And then once we were happy with that, then the data set was then organized and documented, and we've now made it available for use on the internet. And I'd like to now go and maybe give you a demonstration of how you would access, or how you can access the data set, and a little guide around what's contained within it. We've already seen in the overall diagram what's contained within it, but I'll give you a demonstration of how to access it. So the landing page is www.NapierOne.com, and you'll be presented with this page. And then if you mouse over and then you click here to access the data set, and that will take you to the data set, which is hosted on AWS, so it should always be available for you. And then the first screen that you're presented with is top of a tree hierarchy. At the top, we have the data, which contains the actual data contained within the data set, and then some associated documentation, including the paper that describes our work and how it was developed and the contents of it, as well as links to other related areas for this data set. So if you click on the data, we come down into the next level of this tree hierarchy. And you may recognize this, as this is the same as the diagram I showed you earlier. It shows the main data types that we have within the data set. And we don't have distributed in this data set, we don't have the individual files. We have compressed archives of the files. And the archives consist of 3 different types, and they're labeled tiny, small, and total. And the tiny archive will contain 100 examples of the file of that type. The small will contain 1,000, and then the total will contain the full 5,000 examples of the file of that type. So for example, if I go to the docx, Here we have several data subsets, and if I find basically the docx small will contain 100 examples of docx files with a sequence number 0001 to 0100. And here we can see some other data subsets related to this docx. So we have a docx file, and we have the docx password, which is the same files as the docx dataset, but each file in this dataset has also been password protected. They all have the same password, and it's NapierOne. But then again, we can see another use for this dataset is you can compare the original file with a password protected file. And we also have a version of the file where the magic number has been stripped out, just also, again, for comparison and for testing of different techniques for identification of file types, etc. Then contained within each of these data sets, there is documentation for that specific data set. So for example, for this docx data set, there's a PDF here with docx, and this PDF describes in more detail the data set. So we have a description of the data set, how many files exist within the data set, the latest version of the virus scanner that was used against that data set to confirm that it was free from infection. Then we have a description of how the data set was created. We have a description of the naming convention used within that data set. We have some contact information. We have information relating to other files related to this data set, and these are related because they're all sourced from the same gov.uk websites. And then here we have provenance, where these are the websites where files in this data set were sourced from. So you can see that we've been around the gov.uk domain quite a lot and gathered a lot of files. I'll get rid of that. So then, for example, we have an extra data set, and here we have the examples of files that also exist within NapierOne, but have been encrypted using different ransomware strains. So, for example, we have from the Dharma ransomware, and we have Maze, and we have NetWalker, NotPetya, Sodinokaby, Phobos, Ryuk, etc., etc. So, for example, in the Dharma dataset, the file that has the 0001 sequence number is the same file that appears in the Maze dataset with the same sequence number, but encrypted with a different ransomware. So it's possible to then compare different ransomware encryptions on the same file. The original file is also in the dataset, so you can see the before and after again. And it's also another area that this dataset could be used for. And so on and so on. Each data set has tiny, small, and total. If you want the full 5,000 files, go for the total. If you want an example or a subset, go for the smaller one. Each data set has its own PDF describing where it was sourced from, and also attribution information. And there's no password or anything to get onto this data set. It would be nice if we had an email from you to say that you're using the data set. It's good for to know that it is being used, but also the uses it's being used for. And also this data set is not static. We intend to maintain it and also update it when and where new file types become available or become needed. Then we intend to add to this original data set. So the data set can be considered a first shot or a first attempt at what we currently use. But as we identify new techniques or new file types, then we will obviously add to it as and when required. And then just coming up a little bit back into the documentation, we have some documentation here about, here's a copy of the original paper that we used. We have external links, so you can go to the Amazon page for this data set. We have a copy to a link to the journal where the paper was published, and we have a link to the GitHub, which is also used to document the data set. And that's pretty much it, really. So I can take some questions, or if Rich or Bill want to answer any questions in the chat.
Yeah. I could go through some of our research if people are still contemplating their questions.
I can throw a question in there just beforehand. Something occurred to me. Are there plans to put an API in front of the data set? I realise that will then be something that needs supporting and managing, but is that kind of in the thinking?
It's not really in the plans, but there, as it's hosted on AWS, there's the S3 bucket infrastructure. So it's possible to interact with the S3 bucket. You can download the whole bucket directly, and that's one way to automate the download.
I think it might be quite interesting if we can automate the use of it, and possibly some updating and things like that. So we've got a few ideas. We just need some students to help with develop some of the projects. But if anyone's got any ideas, we're also interested in that too.
Cool. No, thanks, guys. Well, certainly if we hear, because some people will be watching this after it's gone on demand, as it were, and if we do start to get questions in from people, we'll make sure they know that there's they can get in touch to take that forward. I think it looks like Ada's asked a question there.
Taylor, I wonder if there's any encryption time differences between a folder tree of each file in the folder being the same type versus a natural file store where this is more randomized. Well, we've got a research project looking at timings, so creating standard file systems with a variety of different files from NapierOne, and then running lots of different ransomwares across these systems and analyzing the encryption times, looking at file sizes, a variety of different kind of behavioral file interaction and file system interaction behavioral stuff. So yeah, that's quite an interesting question. There's quite a few of the newer ransomware strains which pick and choose which encryption they're going to use, even on the fly. So they might use different encryption on different sizes of files even. You can configure a lot of the new ones to do different things. Some of them look to see what types of systems are running on, choose different encryption methods. They'll choose different encryption methods for larger files. They may only encrypt parts of the files. So it's quite hard to compare like with like sometimes. So there's some interesting research opportunities there. We've got a couple of students working on that currently. So I could quickly go over some of the kind of general. So this slide's some of the sort of general research we've looked into, and some of the most common research that's around at the moment. I mean, there's a vast amount of research started in this area in the last couple of years. It's hard to keep up, to be honest. So it's a great area to work in, and there's lots of interesting things. So I've kind of split it into three. Analysis of ransomware and its behavior, detection and kind of mitigation, prevention, recovery. So yeah, the first one covers a large area, and it's a lot to do with the type of thing that associated with the question there. So looking at behavior, so looking at ransomware behavior, static dynamic analysis of ransomware, looking for features. So lots of different things, generally towards detection. But also kind of wide-ranging dynamic behavior analysis. So as I said, looking at how ransomware behaves with the file systems and different types of files and different operating systems and in different environments. Mostly recording things towards detection, though. So also looking at things like ransom note creation. So there's a lot of detection solutions being worked on just for things like ransom notes and how the ransom notes are created, what they look like, how they appear in memory and on the disk, and things like that. Crypto management. So there's a huge amount of research around crypto management and how ransomwares use cryptography and how they create keys and how they do a multitude of different types of encryption to hide those keys and to protect the owners of the ransomware and the middle men that they sell the ransomware to, etc. And detection usually based around these sort of things. So, using things like ransom notes, file changes, network analysis, file entropy, hybrid models of all these different types of features, machine learning, so taking a lot of features in, modeling, and then kind of prediction for future ransomware, kind of proactive and reactive as well. So looking at pre-ransomware encryption stage, before the ransomware starts its nasty business. Once it starts its encryption and execution, there's a lot of research into that area. So looking at file changes, entropy, we're looking at things like memory and API calls, crypto API functions and things like that. There's a lot of research into that. So there's some promising solutions. Hybrid detection seems to be the most promising solution. So using more than one method, more than one set of features. And then mitigation, there's been some mitigation, prevention, recovery. There's been some research into that, but a little bit more limited. So it's quite hard to do. So there is some successful stuff around API function capture and pulling keys from API use. So when crypto APIs are used, grabbing the keys and storing them off. But the only solution that in the research at the moment that seems to work for that is preventative based on the amount of processor it uses and the time it takes. So we've got some interesting solutions into that as well. But generally, the issue with all of this research is the data sets aren't distributed or even described properly. So I would say, I think we reviewed the kind of 12 most referenced ransomware kind of tools that have been created in research. So the 12 things that they think have been the best solution so far, not one has a data set that's described or you can use again to compare against. So that was, our kind of justification or some of our drivers for creating, for Simon doing all the work on this data set. So it's very important. And we've already had it starting to be used kind of thing. So that's good too. So this is some of our research. So along the same kind of lines, analysis, as I said, we've got some analysis looking across things like ransomware interaction with file systems. We've also got some kind of behavior analysis looking at things like memory artifacts and memory interactions, which has got some interesting kind of detection uses. Mostly we're running things across various kind of file system kind of data sets which have been created from NapierOne. So we can kind of define all of these things. So if we produce a set of features or a set of analysis, we can also produce the data set it was created from. So if another version of the ransomware or a different family wants to be tested, then we can compare, etc., which is a bit more useful than some of the research at the moment. So things like directories, sizes of file, ransom note creation, things like that. So being able to run things and create feature sets is quite useful for detection. In terms of detection, we've had some work published. So Simon, myself, Bill, have worked on some detection mechanisms based on previous work, building on those. So we've been successful in creating entropy-based detection around file changes. So once the ransomware starts encrypting files, being able to detect entropy changes, and not only high entropy, so encrypted files, but the difference between files being encrypted by ransomware and other common high entropy files such as compressed files. So Simon's managed to create quite a successful technique, which we had published recently. So that's very promising. We're looking into machine learning modeling, hybrid systems as well for detection. So looking at various features, looking at memory artifacts. So we've got several pieces of work around that area at the moment. And hybrid does look like the best idea, even if it's hybrid machine learning. So some of the most recent research is using multi-layered and hybrid machine learning. So ransomware's evil. I'm just having a look at the chat there. Yeah, so network analysis as well. Network analysis is promising for preemptive. So we have one research project looking at kind of proactive detection before the encryption starts. So there's some quite new research into modeling all sorts of different features pre-encryption. So basically taking everything before the encryption starts and attempting to use those features for detection. So it's quite interesting. And mitigation and recovery. I think Simon undersold some of his previous work in his presentation in that Simon and I came up with an idea about pulling keys from memory a few years ago as part of his MSc project. And Simon was the first person to successfully pull ransomware keys out of memory and decrypt files. So basically using a kind of side channel attack, looking at memory and pulling keys out. So we successfully managed to pull out keys for some current ransomware strains about 3 years ago, and detect and decrypt the files. So that was when ransomware was kind of like one key per victim type ransomware. So it's a little bit older, but yeah, we published that, and I mean that was a success at actually decrypting files without any master keys. So not using the sort of normal ways of decrypting or decrypting tools that you might have seen. So we've got some ongoing work looking at a variety of sort of memory forensics, similar types of memory forensics on newer ransomwares, with some pretty good success at the moment. So keep an eye out for those publications coming out soon on some of our recent stuff there. And just to kind of finish off, I'm going to find my slides. Yeah, so we have got some interesting ideas around the data sets. So it'd be interesting to hear if anyone's got any interesting ideas for research work around what we've discussed, and also for the data set. So keeping the data sets up to date is obviously a bit of a job. So we've got some automation ideas around that, but we've also got some ideas for adding to the data set. So as I mentioned there, around behavioral research, it'd be interesting to add maybe automated kind of image creation or data set creation that other people could run ransomware and do other experiments on. So creating kind of template images maybe for different types of users and file systems and things like that. We have got some ideas around some standard data sets from the output. So running ransomware across some of our fixed data sets of files and such like, and producing some feature sets. So maybe sets of memory artifacts, sets of file interactions and such like. Even network behavior was mentioned in the chat there. And maybe storing those alongside some of these template data sets. So we've got a couple of projects looking at that at the moment as well. And I've got some pretty high-flying ideas around automated analysis of new families and variants, you know, which would be useful for keeping the data sets up to date, but also, yeah, if you could press a button and basically analyze all the latest variants, that would be fantastic, and produce some of these automated data sets would be great. So yeah, interested to know if anyone's got any ideas or opinions. So I mean, contact us separately as well. Have I missed anything out?
No, I don't think so. But you just need to remember www.NapierOne.com.
That's it.
Thanks, Simon. Thanks, Rich. And there was one question. What has been your biggest challenge when conducting the ransomware research? Was there a particular? I think there's various things you've touched on through the presentation, but was there one particular challenge that was, or maybe it continues to be a challenge in the research?
I think initially the challenge was, what is a common file type? Because there are literally hundreds of thousands of file types. And some of them are obvious, like PDF and docx, but when you come out of the top 10, it becomes a little bit more, it depends. It starts to depend what industry you're working in. Yeah. So if you work in a design studio, then the graphics types of file types are more important. Or if you work in engineering, then maybe data-based file types.
Okay. No, thank you, Simon. And a question, I guess, for anyone wanting to use the data set. You've mentioned it's there and you can download the whole S3 bucket. Are there any sort of licensing constraints around it, or anything that people need to be?
It's free. It's free for use, for academic use. If you're going to use it in more business related aspect, it'd be nice if you contacted us first. And if it is used, then just attribute the data set to us in any printed publication or research work. The attribution details are in the documentation of the data set, so it's just a copy and paste, basically.
Right. Oh, okay. Well, we will obviously encourage people, whether they're using it for academic or commercial purposes, to get in touch, because it's always good to share that knowledge. Hear more about where your research is going. So yeah, thank you. I mean, I come from a software engineering background, and developing new capabilities. The hardest bit is always finding representative data sets to test and verify solutions against. So this is very, very welcome. And yeah, thank you ever so much for your time. And thank you,
Pleasure.
Rich and Bill as well. As we get more questions, which I'm sure we will, we'll make sure we send them your way offline. And yeah, those of you listening and tuning in, thank you for your time today. Some great questions there, and we'll be in touch in the not too distant future with our next tech showcase. In the meantime, take care, and we'll see you all soon. Thanks a lot.
Thanks very much.